we're going to look at it together anyway. So we're going to look at structure of alkenes and alkynes. If you remember from quiz 2, which reminds me, I have that to give back to you. Heard that after class. So from quiz 2, you had to define those. So alkenes are double bonds, alkynes are triple bonds. And in this chapter, we're going to look at some of the shapes and the structure, which we'll do today, and then we'll get a little bit into the naming. Naming of alkenes and alkynes is not going to be on the exam on Wednesday, but it will be on the next quiz and on the next exam. So just to kind of get started with it, you can probably figure out where this is going, but for naming, this is called ethene, and this is called ethyne. You'll notice those are both 2 carbon groups. And what's changed is the suffix, the end of the word. So we had ethane with an A, which was the alkane, CH3CH3 or C2H6. Then we have ethene, the alkene, C2H4. And then we have ethyne, the alkyne, C2H2. So when we get into more naming, that's how we're going to name these things. Instead of talking about the substituents, we talk about actually changing the end of the name to "ene" or "ein." So if we, to kind of review this stuff, what's the hybridization of the carbons on ethene? sp2. Good, thank you. And ethyne is sp. So that means that double bonds are going to have 120-degree bond angles, triple bonds 180-degree bond angles. So sp2 carbons, alkenes, are generally planar, meaning they are in the same plane, because if you have 120-degree bond angles, you don't get this kind of zigzagging pattern. You actually get a flat, kind of a tile-like pattern, flat hexagon. All right, so let's take a look at the internal structure of these things. I'm going to copy a picture over from the book because if I try to draw it, it's not going to look great. So this is page 105. All right, so if we think about the orbitals of what's going on in these molecules, so here's our alkene. If you remember from Gen Chem, each carbon is sp2 hybridized, which means it's going to have 3 sp2 hybrid orbitals. So those 3 sp2 hybrid orbitals are here pointing toward the other carbon, here pointing out toward one hydrogen, and there pointing out toward the other hydrogen. So those are the sp2 hybrid orbitals. And since there is one s orbital and 3 p orbitals, that means there's a third unhybridized p orbital. So a p orbital that is not part of the hybrid orbitals, that is pointing straight up, orthogonal to the hybrid orbitals. So there's this extra p orbital that's not hybridized. And it's that p orbital that makes that second double bond, because the other carbon is doing the same thing. So those leftover p orbitals make what's called a pi bond. So you have a sigma and a pi bond. You have the sigma bond from the overlap of the sp2 orbitals, and you have the pi bond from the overlap of the p orbitals. Remember also that a pi bond is a kind of a two-sided bond. So I drew those two interactions. That's not the double bond, that's just one of the bonds. The other one is right here, the sigma bond between the two carbons, between the two hybrid orbitals. So the two orbitals in a double bond are a sigma made of two sp2 orbitals and a pi made of two unhybridized p orbitals. That pi bond is what explains the fact that double bonds don't rotate. So we did all this stuff with conformations, but when we look at double bonds, which we can make in this kit with these curved things, oops, that's the wrong shape. So we can use these curved shapes to make double bonds. Add our hydrogens, and we have something like this. And now it is fixed. It no longer rotates. And that's what's happening in the actual structure as well. The pi bond stops this from rotating because if it were to rotate, those p orbitals would no longer be parallel. And if they're no longer parallel, they can't interact anymore. So it's not that a double bond can't rotate, it's that it takes energy to break that bonding interaction. So at high energy, yes, you can rotate double bonds. But at kind of standard stable conditions, it's always going to be more stable if those double bonds can be parallel so that they can have that interaction, that bonding. So that's what gives rise to that property. So we don't talk about conformations and such with double bonds. The other thing that causes then is a type of stereoisomerism in double bonds that we don't have with single bonds. So if we look at butane, we would draw butane like that, but we could also draw it like this, and we would say those are the same. Or I guess more accurately, we'd say they're conformers. They're different conformations. We would say the one kind of over on the left is a little more stable because those methyl groups wouldn't be close to each other, but both of those are conformations of butane, and we know that's always kind of rotating, and we just talked about all that stuff. If instead we look at butene, which would be 2-butene, has the double bond here, these are not the same. This is what we would call stereoisomers. And they're not the same because that double bond can't rotate. So if I put two methyl groups on like that, let's say those are my carbons, I can't rotate that. There's no way I can get to the other isomer unless I take one off and actually switch it, put it on the other position. The reason they're stereoisomers and not constitutional isomers is both of these are butene. They're called 2-butene, and we'll talk about that naming later, but they're both called 2-butene, but they're definitely different. So we need a different way of describing those, and the way we describe those is cis and trans, just like with the rings. So this one is going to be trans to butene, and this one's going to be cis to butene. So alkynes, the triple bonds, same idea, just kind of more so. So there actually isn't a picture in the book, but if we use that same kind of idea, instead of sp2 hybridization, we have sp hybridization. So let's see if we can just draw it it's maybe not going to be beautiful, but if we look at our two carbons, each one is going to have two hybrid sp orbitals. So those are our sp orbitals. And there's only two of them, so they're on opposite sides of the carbon. And that means that there's two unhybridized p orbitals on each carbon. So there's one up here. And then there's another one that's kind of like coming out at us and going back behind. So the bonding in a triple bond is you have that sigma bond in the middle of the two sp orbitals. And then you have a pi bond between these two p orbitals. And then you have a second pi bond between this other set of orbitals. Why is that disappearing? Okay. So there's our second pi bond going back behind. So that's what a triple bond would look like. So do you think a triple bond can rotate? Right, also no. But it doesn't matter so much for a triple bond because of the 180-degree bond angles. It wouldn't change the structure at all by rotating. It was already kind of straight. So there's not a top and a bottom to be cis and trans on the other sides of the double bond. To remember, if we go back to the alkene here, to remember the difference with trans and cis, one thing that I think is helpful is to draw a dotted line through or parallel to the double bond and then look at what results. So if we draw a line like that and like that, we can see that on the trans structure on the left, those other groups are on opposite sides of that line, and on the cis structure, they're on the same side of the line. So you know trans means opposite, cis means the same. So you've got opposite sides, same sides. Which do you think is generally more stable, the trans or the cis isomer? If you were going to guess. Trans, yeah, why? You're right, why? Right, yeah, so there can be kind of more space for those larger groups, depending on what they are, to be spaced out. And you can imagine the bigger those groups are, the bigger the difference between trans and cis becomes. So the last thing we're going to say is when we draw line structures of these things, there's a couple different ways we can do it. So double bonds, generally, if we're drawing some big structure, you're generally going to draw whatever you're going to draw, and then you add the double bond just by adding a second line. It doesn't really matter where, I mean it matters where it is depending on what structure you're drawing, but like which side of the thing you draw it on, that doesn't really matter. But usually you'll see them drawn more like this than, let's say, like this, where it would be like a separate kind of a double bond looking thing. Usually that top one just looks a little nicer. You just kind of fit that double bond right inside of it a little bit. With triple bonds, because of the 180-degree bond angles, we don't zigzag the triple bond. We find the different carbons by the ends of the triple bond. So, and I think we saw that on the last quiz too. So if you have a structure like this, we're going to draw it like this. We're going to take our triple bond, and that's going to be those two carbons. And then here's the next one, and here's the next one, and the next one. So to number this, if this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The two ends of the triple bond give us our two carbons. We don't zigzag it because we know that's not the correct bond angle for the triple bond. These triple bonds are linear. You can have a triple bond in the middle of a structure also, and you do the same thing. Whatever the structure is. So that shows the two sides of it, the two carbons in that triple bond. All right, we've got about 5 minutes left. We're not going to go through anything else new. I want to give back what's the deal with the new quiz? I want to give that back. I want to give back your quiz 2, and I want to mention a couple common mistakes that I saw in this one. Most of you did great on these. The one at the bottom?
Yeah.
7. All right, so just a couple things on this quiz. Oh, I didn't make any extras in this one. All right. Sorry, I didn't make any extras. Let me look over somebody's shoulder here. So, thank you. All right, so a couple of common things that I saw to watch out for. On number 1, on C, most people got that one, but be sure that when you're drawing line structures, don't cut the hydrogens off of non-carbon atoms. If it's not a carbon, you have to show the hydrogen with it, so that N has to be NH, not just N. That's actually a different structure. All right, so then number 3B, that's kind of what we were just talking about. There's a carbon on either side of that double bond. A lot of people missed so that's a 4-carbon structure. So a lot of people missed that second carbon on the other side of the double bond on part B there. So watch that. All right, number 5. This one was also, there was a problem there for a lot of people. Saturated and unsaturated has to do with the number of hydrogens, not the types of bonds. So for instance, a lot of people said, that saturated hydrocarbons only have single bonds and unsaturated hydrocarbons have double and triple bonds. That's not quite true. It's true that double and triple bonds make things unsaturated, but you can also have an unsaturated carbon by using a ring like this. So this is C6H12, whereas the saturated version would be C6H14. So any number of hydrogens that's less than 2n plus 2, that's CN2H2n plus 2 formula, any number of hydrogens less than that is unsaturated, whether it's rings or whether it's double bonds or triple bonds. Yes? Yeah, that's not quite right. Because I think that the cyclic ones would also be considered unsaturated. Where does it say that? That's interesting. Okay, well I will I'll change that if the book says that. Oh, it's probably number 3, right? I don't know. We can look for it. It could be that could be the case. They may use a slightly different definition. But anyway, okay. And then the last one was that that one about the number of chlorination sites. This is one of those visualizing things in three dimensions questions. Come on, stop. If we look at this structure, there's actually only two different positions on this structure. This one and this one. Any other position can be related to one of those two by flipping or turning because there's so much symmetry in that structure. So you can imagine anything on the left ring can be converted to anything on the right ring, and then top and bottom also are the same. So anything on the top has a counterpart on the bottom. The very middle carbons would be a different spot, but you can't put anything on there because they already have 4 bonds on each of those. So there's only 2 different positions. All the other positions can be related to one of those by flipping or turning the structure. All right, so we are out of time. Please let me know if you have more questions. Otherwise, happy studying. On Wednesday morning, we'll do a group activity, kind of practice some last-minute stuff for the exam. We're not going to do anything new. Of course, if you have questions, we'll have plenty of time for that also. And I will be around tomorrow afternoon for office hours if you have some last questions. And you can always send me emails. Yeah. One of 3, yeah. Yep.
Can I give this to you, or is it going to be too big of a pain in the rear for you to take to your office?
No, I'll get it. Thanks.
Thank you.
Yeah. Hope it was helpful. You don't need it anymore?
No, I'm good.
Okay.
Can I ask you 2 questions here?
Yes.
All right, so I can see this way. I don't know if this is considered horizontal or vertical. So I can see this one axis.
Okay.
I don't understand how this is the same because if I fold it, there's another double bond here that this one does not have.
Yes. So because of resonance, there's a second equivalent way to write that structure. So in other words, can you borrow your pencil?
Yeah.
So this is written like this, but you could also write this like this. That's an equivalent same structure.
Okay, but then how is this and this the same? Is what I'm saying, because to me here, what I see is this has 3 bonds, or 3, like,
Yep.
right? But this over here does, I
Also
guess
has
it
3,
does
right?
have 3. Oh, fuck.
So remember that, in fact, if you look up the structure of an naphthalene, remember that these are kind of, that resonance means averaging. So if it's going back and forth, that means that the actual structure is kind of an average of all of these, which we don't usually write like this, but we could kind of imagine it as just like those double bonds being distributed all around,
Okay.
as like, kind of like half.